We're going to take a look at how to evaluate a limit analytically, meaning using properties of algebra to finally come up with a result. But before we do that, we need to take a look at a few properties of limits to help us. Now these end up being very useful when we're trying to evaluate a limit. So here's what they are. We're just going to put a couple up here and then I'll explain. Let's say we do the limit as x approaches c of some constant times a function. So basically here this is just a constant times some function of x, kind of like 4x squared, right? The 4 is a constant multiple. Well, believe it or not, hold on, an eraser. When we are evaluating a limit and you have a constant multiple, the constant multiple actually does not affect the limit. You can actually just do the limit of the function of x and then multiply it by that constant. If we're doing the limit as x approaches c, what if we have two functions, say f of x plus or minus some g of x? Well, if you have things joined by addition or subtraction, kind of like x squared plus 5x, what you can actually do is just do the limit of each one of those functions. So this is the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. Let's see, no, this also works for if we're doing the limit as x approaches c of f of x times g of x. If you're doing the limit of two things joined by multiplication or the limit of a product, that just ends up being the limit as x approaches c of f of x times the limit as x approaches c of g of x. So that's quite helpful also. And let's do this last property. If we're doing the limit as x approaches c of f of g of x, basically one function inside of another function, you can actually do this ends up becoming the limit as x approaches c of g of x. Basically, the limit can pass through any what we call continuous function to get to the inside. All right, so there's four properties, and these are very, very useful. I know they're a little bit confusing right now the way that they look with all this notation, but we're going to see how we use these coming up. All right, let's take a look at evaluating. I'm going to put this over here. Evaluating limits. Now, when we're evaluating limits, we're going to kind of go down a list of what we want to try. The first thing we want to try is something called direct substitution. Now, here's the idea behind direct substitution. Let's see if this makes sense at all. If a function is continuous, now there's a mathematical definition of continuous that we'll get to either this lecture or the next one, but the idea for continuous when we're talking about some function is, can you draw it without picking up your pencil? And you see something like that would be continuous. However, a graph that looks like, I don't know, you came across and you jumped down here, right? That's not continuous because you still had to pick up my pencil there. So that is not a continuous function. However, it is continuous over here and it is continuous over there, but overall not a continuous function. This is a continuous function, which means kind of the idea is one point kind of flows into the next as you move through it. That means if I want to find the limit in any value here, well, since it's continuous, that y value will just be the function value there. So if I'm looking for a limit and I know that the function is continuous, basically it exists there, really all I got to do is plug the value into the function to get the y value. This is called direct substitution. This is what you always want to try first when you're evaluating limits. So for direct substitution, let's just take a couple quick examples here. Let's say if I said the limit as x approaches 5 of 2x minus 3. So what's the limit of this function as x gets closer and closer to 5? Now remember, technically that's really two questions. The limit from the left, the limit from the right. But I know that the graph of this is just a line. Now, I know a line is continuous everywhere, so kind of like this idea, the value of the function at that spot will be what the limit is, right? Because it's continuous. One point flows right into the next. So really all I got to do is direct substitute in here. So plug 5 in for x, and we get 7. So since we got a nice value out, we can say that this limit exists, and the limit is 7. Or if we had something like the limit as x approaches -1 of x squared plus 2x minus 4. Again, we always want to try direct substitution first. I know that this is just a parabola. I know that's continuous everywhere. And so if I plug this value in, I should get a value out. So if I plug -1 in there, it's -1 squared, 2 times -1 minus 4. Now remember, anytime you're plugging a value into a function, make sure you're using parentheses. So if I simplify that, -1 squared is 1, 2 times -1 is -2 minus 4. That's going to be -5. Okay, so the limit as x approaches -1 of x squared plus 2x minus 4 is -5. So this is great. It's super quick and easy to evaluate a limit if you can use direct substitution. Well, like all things in life, of course, it's not always that easy. Direct substitution doesn't always work because you don't always get a value out of the function. Let's continue along these lines. What if I said the limit as x approaches 3 of x squared minus 9 all over x plus 3? Now, I believe this is the one we did last lecture, and we saw on the table, by plugging in all those numbers, we saw that this was, actually I had -3, probably. It was -3. We saw that it was 6. And we did that because we plugged it all in the calculator to do it. Well, we can actually see it's a little bit easier to do. We do always want to try direct substitution first. And if you see, if we try direct substitution here, we end up with a problem. We end up with 9 minus 9 over 3 minus 3, or 0 over 0. Now, the question is, what is 0 over 0? A lot of people want to say it's 1, right? Because anything divided by itself is 1. Some people say it's 0 because 0 divided by anything is 0. Well, believe it or not, the answer to this is 0 divided by 0 can be anything. Anything at all. It can be any number. And it may not even exist. You can kind of see this. The reason this is true is because 0 times anything is 0. Now, I know we're not allowed to divide by 0, but notice if we divided both sides by 0 here, on this side we'd have 0 over 0 equals anything. So you can kind of see how that relationship is true. So since we have 0 over 0, we have no idea what value that is. So when we're doing direct substitution, if you get 0 over 0, you got some algebra to do. So we should be able to rewrite the original expression so that we can simplify it. Now, one of the first things that we learn how to do when simplifying these is to factor. I'm going to go and put this down here. First thing you may want to try is factor. Notice the top here is the difference of squares. That'll factor to x plus 3, x minus 3, all over x minus 3. The x minus 3's can reduce, and if you notice, the x minus 3 is actually the problem because that's what's becoming 0 as we get closer to 3. So if we reduce that problem spot out, and we do the limit as x approaches 3 of x plus 3, now notice I can evaluate this, right? I can do direct substitution here, and I get 3 plus 3, which is 6. Which of course is the same answer we got from our table from the previous lecture. But the question is, I answered the question, what's the limit as x approaches 3 of x plus 3, and I got 6. But the question was, what's the limit of this function? Those look like two completely different functions. So what is the relationship between those two? How do I know that one answer to this even applies to that at all? Well, the good news here is technically this is a rational expression. And when we end up with 0 over 0 in a rational expression, what you end up with is a hole in the graph. The only difference between these two graphs, if you were to graph them, right? This is a line with a slope of 1 and a y-intercept of 3. So it would look like this. This is y equals x plus 3. If you were to do the exact same thing and draw the same line, the only difference here, is in between these two graphs, at 3, this one is continuous. This one has a hole in the graph, but they look exactly the same. If you don't believe me, grab a graphing calculator, grab a computer and graph both of those, and they'll look exactly the same on your graphing calculator because remember, this hole is infinitely small. It's not really that big. All right, so anytime you're doing evaluating a limit, you always want to try direct substitution first. If you get a number out, that's it, you're done, it worked. That's your limit. However, if you get 0 over 0, you got some more work to do. Now, one of the first things you want to look to do is factoring like we did here. This is going to happen quite a bit. Another technique that may show up, let's take a look at another limit. Let's say I did the limit as x approaches 9 of the square root of x minus 3 all over x minus 9. All right, so this is a limit problem. We're told to evaluate this. So the very first thing that we would want to try is direct substitution. And you see if you plug that into the top and the bottom, that's going to give you 0 over 0. So as soon as you see 0 over 0, you're thinking, I got more work to do. Now in this case, technically we can factor this, but generally when we see radicals involved, one of the things we're going to want to look for is rationalizing. Now in the past we've seen we generally rationalize the denominator, but here we're actually going to rationalize the numerator. Now remember, rationalize just means get rid of a radical. So when we saw this, when we were rationalizing the denominator of things, we would multiply the top and the bottom by the conjugate of the piece that had the radical. So this piece has the radical. The conjugate, remember, is the same two pieces, but with a different sign in the middle. So I'm going to multiply the top and the bottom by the square root of x plus 3. Now, here's a little bit of a hint for you when you're rationalizing things in these cases. Don't multiply out the one that you're not rationalizing, right? I'm rationalizing the top. Keep the other one the same. You'll see why in just a second. Now, when I start distributing here, technically this is the difference of squares. You would get what? Square root of x times the square root of x, which is x. That's going to be plus 3 square roots of x minus 3 square roots of x. So that goes away. Minus 3 plus 3 is minus 9. So once we rationalize the top here, notice that we end up with x minus 9. We also have that on the bottom. That's why I told you not to multiply it out. That will reduce now, and we end up with the limit as x approaches 9 of 1 over the square root of x plus 3. Now notice what we canceled out. We canceled out the x minus 9, and that's the piece that was turning into 0 as we got closer and closer to 9. So we got rid of the problem spot, so now what we got to do is try direct substitution. When I do direct substitution, I get 1 over the square root of 9 plus 3, which would be 1/6. Okay, so we always try direct substitution first. If we get 0 over 0, we want to try some algebra. Factoring shows up a lot, and so does rationalizing. You can either rationalize the numerator or the denominator, depends on where that radical is. Remember, you're always going to be using the conjugate. So we're going to see another case in the future where we end up with something else we got to watch out for. We'll see that in a future lecture.